Have you ever watched sunlight passing through a glass ornament and noticed a rainbow forming on the wall? That magical split of light is thanks to something called a prisma. A prism is a transparent refracting medium, usually made of glass, bounded by 5 flat surfaces. 2 of these are triangular faces, equal and parallel to each other, while the other 3 are rectangular faces inclined to each other. The 2 important ones for us are the refracting surfaces, the faces through which light enters and leaves the prisma. The angle between these 2 refracting surfaces is called the angle of prisma, and it plays a big role in how much light bends. The line where the 2 refracting surfaces meet is the refracting edge, and at the bottom we have the base, which is usually rough so the prisma can stand steadily. As you can see in the diagram, every part of the prism has a specific function that influences the behavior of light passing through it. To understand refraction through a prism, we often simplify it by looking at what's called the principal section. The principal section is like slicing the prism along a plane that's perpendicular to its refracting edge. This gives us a triangular cross-section, usually labeled as triangle ABC in diagrams. The angle at vertex A between sides AB and AC is our angle of prism A. These 2 sides represent the refracting surfaces. By focusing on this section, we make the analysis of refraction much easier because we reduce a 3D shape into a simple 2D triangle without losing any essential optical behavior. Now let's follow a ray of light as it passes through the prisma. When a ray enters from air into glass at the first refracting surface, it slows down and bends towards the normal. That's our first refraction. Inside the prisma, the ray travels until it hits the second refracting surface. Here, it moves from glass back into air, so it speeds up and bends away from the normal, the second refraction. The ray that finally emerges is called the emergent ray. If you observe its direction, you'll see that in both refractions, the ray bends towards the base of the prisma. This double bending is what causes the change in the ray's overall direction, something we call deviation.
One of the beautiful principles of optics is the principle of reversibility of light, and prisms are a perfect example of it. This principle says that if a ray of light follows a certain path through a medium, it will follow the exact reverse path if its direction is reversed. So if we send a ray along the emergent path, it will retrace its journey and emerge from the original entry point. This happens because the laws of refraction work equally well in both directions. Optical engineers use this property for precise alignments in instruments like periscopes and binoculars. Now, let's define something very important: the angle of deviation. Imagine this. If there were no prism in the way, a light ray would continue in a straight line, completely undisturbed. But when we place a prism in its path, the emergent ray comes out in a different direction. The angle formed between the original straight line path and the emergent ray is what we call the angle of deviation, denoted by delta. This deviation can actually be broken into 2 parts. The first is the deviation at the first surface, delta 1, which equals the angle of incidence minus the angle of refraction, written as delta 1 equals I minus R1. The second is the deviation at the second surface, delta 2, which equals the angle of refraction at that surface minus the angle of emergence, written as delta 2 equals R2 minus I2. Here, I is the angle of incidence, R is the angle of refraction inside the prism, and I2 is the angle of emergence. Finally, the total deviation is simply the sum of the 2. Delta equals delta 1 plus delta 2. So, in essence, the prism bends light twice, once when it enters and once when it exits, and together these bends give us the total angle of deviation.
Let's apply this to a numerical problem. We are given angle of incidence, I, equals 40 degrees. Angle of refraction at the first face, R1, equals 25 degrees. Angle of incidence at the second face, R2, equals 35 degrees. Angle of emergence, I2, equals 50 degrees. Step 1. Calculate delta 1. Delta 1 equals I minus R1, that is 40 degrees minus 25 degrees, which equals 15 degrees. Step 2. Calculate delta 2. Delta 2 equals R2 minus I2, that is 35 degrees minus 50 degrees, which equals negative 15 degrees. The negative sign simply tells us the direction of bending at this face. Step 3. Now find the total deviation. Delta equals delta 1 plus delta 2, that is 15 degrees plus negative 15 degrees, which equals 0 degrees. This is a special case where the ray emerges undeviated, and this happens when the incidence and emergence are perfectly symmetric.
Let's quickly recap what we've learned today about prisms. A prism changes the direction of light through two successive refractions, and the amount of bending depends on its angle and refractive index. Inside the prism, the light always bends towards the base, and we measure its shift using the angle of deviation. We also saw that the principle of reversibility ensures the light path works both ways, and we applied these ideas to solve a numerical example. So the next time you see sunlight dispersing into colors through a prism or a piece of glass, you'll know the exact physics behind it. I hope this session helped you understand how prisms guide light, not just in classrooms but in cameras, telescopes, and even in your phone's optical systems. See you in the next topic.